This week we discuss about diffusion. So we are going to do some tutorial questions. I hope you remember the theory. I will explain the theory that needed to do the questions, but there are a lot of theory in the diffusion topic in week 5. Okay. What do we mean by diffusion? Are we using it in day-to-day life? Where? Okay. We enjoy the smell of coffee, am I right? And also you use perfume to smell you nice. So that's applications of diffusion. So diffusion is the mass transfer from high concentration to low concentration. So we are going to discuss about 2 types of diffusion, steady state and non-steady state. When you look at the diffusion, if we summarize the things that we have done in the lecture, so we know what is diffusion now. Diffusion mechanism, diffusion can happen through vacancies, vacancy diffusion. So you already know what is vacancies. What are vacancies? Am I right? So when we have vacancies, that vacancy can be filled by another atom. So likewise, the material can transfer from a high concentration to low concentration. And also diffusion can happen in interstitial diffusion via as interstitial atoms. Small atoms can squeeze in between the big atoms, so that we call the interstitial diffusion. This diffusion is influenced by the temperature, diffusion coefficient, and also the activation energy. As I have mentioned, we are going to do questions on steady state diffusion and also non-steady state diffusion. So steady state diffusion means, so we discussed already, diffusion is happening from high concentration to a low concentration. So for example, here, you have a concentration of something, maybe nitrogen in one side. So that is your concentration 1. So nitrogen can diffuse to another material, and here maybe the concentration is C2. So steady state means this concentration at a point, certain point. For example, if you consider the concentration of nitrogen at this point, it will be a constant. It's not depending, it doesn't depend on the time. So there is a concentration gradient from this side to the other side, but that when you consider a certain point, that concentration in that particular point is not changing with the time. So concentration gradient is only changing with the distance, that this distance here, but not with the time. So that particular situation we call the steady state diffusion. For the steady state diffusion, we can apply the Fick's law of diffusion, and that equation is this one. J is equals to negative D, dC over dx. Here, J is the flux, D is the diffusion coefficient, C is concentration, and X is the distance measured from a certain point. So when we discuss, we are going to do a question, so you will understand more about these terms when we do the question. Okay. So in the seconds, in the non-steady state diffusion, we can apply the Fick's second law of diffusion. So we need to consider the second derivative. Here you can see this is the equation that we are going to use. In that one, the concentration at a certain point is changing with the time. For example, when you consider temperature is equals to T1, you have, so you have concentration at this point, as I have shown here, and with the distance, the concentration is changing like this. So this is when the time is equals to T1. If we consider after some time, maybe the time is equals to T2, the concentration is changing like this. So you can see the concentration is changing not only with the X, it is changing with the time as well. Does that make sense? The difference between steady state and non-steady state, when the time is equals to T3, the concentration gradient will be like this. So you can see the concentration is changing with the time. So after some time, maybe the concentration will be equal for both the sides. Is that make sense? The difference between steady state and non-steady state. Any question? No questions? Okay, for the non-steady state, we are going to use this equation. With your maths knowledge, you can solve this. Am I right? However, we are going to use the simplified solved version or the simplified version of the equation when we do the question. So we have one question from steady state. We have another question from non-steady state. And also, when we discuss about the diffusion coefficient, so you have this diffusion coefficient for both the steady state and non-steady state diffusion equations. However, this diffusion coefficient is not a constant. It is depending on the temperature and also the diffusion species. If it is nitrogen in steel or carbon in steel. So depending on what species that we are looking at, the diffusion coefficient will be different. And also with the temperature, the diffusion coefficient will change. Okay, so it's a function of QD, which is activation energy, and also the temperature in kelvins. Okay, so we can find the diffusion for a certain temperature, for a certain material using this equation. Does that make sense? Okay, so these are the three equations that we are going to use today for the questions. Before moving to the questions, do you have anything to get clarified? So this summarizes the things that you have done in the lecture. There are other things as well you may need to go through. Do you have any questions so far? No? So this is our first question. So here they say a sheet of steel 1.5 millimeter thick has nitrogen atmosphere on both sides at 1200 degrees Celsius and is permitted to achieve a steady state diffusion condition. So we are looking at a steady state diffusion condition. The diffusion coefficient for nitrogen in steel. So as I have mentioned, see, nitrogen in steel, for this particular temperature, the diffusion coefficient is given to us, which is 6 times 10 to the negative 6 meters squares per second. And the diffusion flux is found to be, so this is the diffusion flux. Diffusion flux is how quickly or else how fast the diffusion is happening. So it's in kilograms per meter square per second. So that is your J. Also, it is known that the concentration of the nitrogen in the steel at the high pressure side is 4 kilograms per meter cube. And how far, they're asking how far into the sheet from this high pressure side will the concentration be 2 kilograms per meter cube. Assume a linear concentration profile. So here you have nitrogen and you have steel here. So nitrogen is diffusing into the steel, isn't it? So they are saying in one side, the concentration of nitrogen. So concentration of the nitrogen is equals to 4 kilograms in a meter cube. And at a certain distance, let's take this one as X distance from here. We measured the X from here. At this point, the concentration is 2 kilograms per meter cube. And they say, they are asking us to find this X. Am I right? So in this equation, if you consider this equation, we know everything. J is known, D is known. So concentration, change in the concentration, that will be C2 minus C1, and that's also known. Change in the distance, so it is going from here to here. So that distance, we took it as X, so that is X. So you in this equation, you know everything except X, so you can make the X the subject and you can find me. So how many meters? We don't have to do any unit conversions, isn't it? Because all are in SI units. So you just need to plug in the numbers and you will be able to find the X. So can I give you a few minutes for you to find the X? D is 6. D is the diffusion coefficient, which is this one. This is D and this is J. So if you make the X subject, that will be negative D C2 minus C1 over J. G is the diffusion coefficient, yes. So that will be 6 times 10 to the negative 11. This will be 2 minus 4 divided by J, which is 1.2 times 10 to the negative 7. So I didn't put any units, but units will cancel out and your answer will be in meters. So what do we get? Is that? Yes, so 0.001. So that means 1 millimeter, isn't it? Do you all get 1 millimeter? Anyone got anything else? Something different? Everything answered? 1 millimeter. Or 0.0. Meters, so that is 1. Oh, 2 minus 4, 1 plus 2. Can I move to the next question? What's that? No, because concentration is 2 minus, yes, final minus the initial. So it is 2 minus 4. No, here for this particular question, no, because temperature is a constant. So when the temperature changes, D will change. But in our case, temperature is a constant. And they have given us this D for this particular temperature and for nitrogen in steel. So D is only changing with temperature and the material. So this is nitrogen in steel. At this particular temperature, the D is this one. So we have another question where the temperature is changing. So in that case, we need to consider the temperature. This 1.5 millimeter thickness is the thickness of the steel. So it's like this. So we have a steel, which is a steel piece, which is 1.5 millimeter thick. And in both the sides, you have nitrogen. So we are looking at the concentration of only 1 millimeter somewhere here. Sorry. Yes. So 1 millimeter, sorry, 1 millimeter is somewhere, yes, at the middle, 1 millimeter thick inside the material. Somewhere here, if you could, sorry. Okay, any other questions? I'll move to the next one. So this question, I have put all the equations that you need here from your lecture note, copy from your lecture note. So let's read the question. Calculate the nitrogen from a gaseous phase is to be diffused into the pure iron. So we have pure iron at 700 degrees Celsius. If the surface concentration is maintained at this particular concentration, 8%, what will be the concentration at 1 millimeter from the surface after 10 hours? The diffusion coefficient for the nitrogen in iron at 700 degrees Celsius is this. So this one should be per second, okay? So this is the D. So D is given to us. D is given to us. D is again a constant because it is the same material, same temperature. But the time, with the time, they haven't mentioned, they didn't say that it is a steady state. So they are saying after 10 hours, what will be the concentration at a certain point. So at 1 millimeter from the surface in 10 hours. Do you understand the question? So if I draw it, it's like this. So you have iron and you have nitrogen here. So at the temperature is equals to 0, you don't have any nitrogen inside the iron bar, isn't it? So you don't have nitrogen, but you have at the surface, you have a concentration of, this is the surface concentration. CS stand for the surface concentration. So that is equals to 0.1 weight%. And then they are saying at a temperature, at a time of 10 hours, now what is happening? This nitrogen will diffuse into the iron. So they are asking us to find from the surface, 1 millimeter from the surface, when the time is equals to, when the time is equals to 10 hours, we need to find the concentration at this point. Am I right? So this we call at a X distance, at 1 millimeter distance, at a time of 10 hours. So this is what we need to find. Do you understand the question? Do we understand the, yes. Weight. W stands for weight %. Yes. By weight, the percentage by weight. Any other questions? No? Okay, now let's see the equations that we can use. So I told you when it is non-steady state. Do you guys have any questions? Are you talking about a question? Yeah. Okay, so can I know the question so I can help you guys? What's that? It's the error function. It's ER stand for error function. I'll explain that, okay? It's the error function. Okay. If you have any question, don't keep ask me as well. Get me involved in your conversation so that I can help you. Okay. All right. So this is the equation that we are going to use. You can simplify this to this one. Am I right? With your maths knowledge, you will be able to do it by yourself. But however, we are going to use the simplified equation. So this is what we need to find, CXT. CS is already known. Am I right? CS is already known, which is 0.1 weight%. Isn't it? C naught is what? C naught is what? When the distance goes to infinite, what will be your concentration? So that will be a 0 here, isn't it? The concentration at a, it will go to 0 because it is pure iron. We are using pure iron at a certain, when X goes to, X is far away, then the concentration of nitrogen in the pure iron will be 0. We need, and what else we know? How about the time? Time is 10 hours. You have time here, isn't it? So time is 10 hours. We need to make it to seconds. So 10 times what? 60 times 60, which is 3,600. What else we know? We know the D, which is 2.5 times 10 to the negative 11 meter squared per second. That's all we know. Okay, so here, if you can find this one here, that part we call the set. If you know that part, you can find this error function using this table. So if you know the z, that means this inside part which I have colored in the equation, this x divided by 2 root dt, if you know that, you can find the error function, which is this. Is it clear? So can you find me this inside part, which is z? Can you find me that z part? This one, that is this part. X divided by 2 root dt. What's that? So x divided by 2 dt, this we call the z. So what's that? X is what? I'll give you a few minutes. X is what? X is what? Yes, x is 0.001. We make it to meters. We have it in 1 millimeter. So that means 0.001 divided by 2. Do we know D? 2.5 times 10 to the negative 11. The time is 10 times 3,600. So when you put this in the calculator, what do we get? 0.527. Do we all get this? Z is 0.527. Do we have that? Yes. X is given to us. See, they are asking at the x distance. So the x distance is 1 millimeter. We converted that to meters, 0.001. Do we all get 0.527? You find this, and if you already found that, you can use the table and find the error function. Make it bigger. No. No, you need, yes. This is, sorry. Okay, so you have in between these two, you can't go to a close value. You need to find the exact value. You know how to do it by interpolation. You need to do by interpolation. Have you done the interpolation in the maths? You learn maths to apply for this kind of question. 0.527, do you all get it? Get it at the back? Yeah. Okay, so now see, if you look at the table, your Z value is 0.527. So when the Z is 0.55, you have error function as 0.5633. When the Z is 0.5, you get 0.5205. So which one? How do we find for this one now? So your error function and the set, how it is changing. When Z is 0.5, your error function will be is 0.5205. When this is 0.55, your error function is 0.5633. So this has a linear, we can assume it is linear here. And we need to find when the Z is 5.527, that corresponding value. So how can we find it? Yes, you consider the slope. Slope is the same. So you can consider slope using, you can write the slope using this triangle. Rise over the run is the slope, isn't it? This tan theta is the same. So if you consider this big triangle or that small triangle, that both should be the same. So you can write rise over the run. So if you consider the small triangle, how do you write the rise over the run? Just take this as y. Rise will be y minus 0.5205. Run will be what? This distance here, which is 0.527 minus 0.5, isn't it? Is that right? And if you consider the green one, big one, rise will be 0.5633 minus 0.5205. That is the rise. And run will be 0.55 minus 0.5. Am I right? So now, can't you find the y now? So this will be, you do by yourself, okay? I'm doing as well to see what we will get. So we can take this to that side. So that will be 0. What do we get? I have written something wrong here, isn't it? 7. Yes, so this one is wrong. Y minus, no, that is right, yes. 0. 0 point? Yeah, just take 3 decimals, 0.544, yes. Okay, so do we all get 0.544? So that is our error function. So this is the error function. Anyone got anything else? Boys, do you get the same? Four. 0.544. Yeah. Okay, that's good. Okay, now we know the error function. And now we can put the error function here. So this is the part we found, which is equal to 0.544. So we know CS, which is equal to 0.1, and this is 0, this is 0. So you can now find CXT. That means in an X distance, at an X distance, with a T time. X is 1 millimeter in our case, and the time is 10 hours in our case. So we already used them to find the error function. So that will be equals to, so this divided by 0.1 is equals to 1 minus 0.5. So this. So what do we get? It is again a weight percentage. Okay, because they have given us the weight percentage, our answer also should be in weight percentage. So it's 0.0456 weight percent. Weight percent, percentage by weight. Concentration, we can have different units depend on what we are talking. Yes, it is given as a percentage by weight. Okay, we are done with the question 2. Do you guys have any question? Yes. Can we move to the next question? Yeah, moving to the next question. Is there anyone still doing? Yes, you can. Yes. C means the concentration, X means the distance. In our case, X is 0.001. Time is the time, T is the time, which is in our case, it is 36,000. We already added, didn't we? We added it. We added this time here and the X distance here when you are finding the. We included that. We found this one at the very beginning. Do you remember? We found it. We found this one. In the equation, it's C times X. No, it's not times. It is for that particular X at that time. So if I show you this one, so you see, do you see this one? So here, see, C is a concentration at X distance. This is your X distance at a time of T. Okay. Okay, question number 3, which is our last question. Here, they are asking us to find the diffusion coefficient. This question is on diffusion coefficient. So the diffusion coefficient for silver in copper are given at 2 temperatures. So you can see when the temperature is 650, diffusion coefficient is this. When the temperature is 900 degrees Celsius, the diffusion coefficient is this. So they are asking us to find the D naught, which is the pre-exponential and also the activation energy. How do we find it? So we have this equation. I already showed you this equation. Diffusion coefficient can be found using this equation. We can simplify that equation to this one as well. So you can either use the top one or the bottom one, both the same. So how can we find this? So in this equation, capital T is your temperature in kelvins. So this we can't use 600 as it is. So 600, we need to add 273. So that will be 923, isn't it? Kelvins. And 900 plus 273 will be 1173 kelvins. So we need to use those temperatures. So if you consider this is your first temperature and this is your first 2 numbers. If you apply those 2 numbers to this equation, you still have 2 unknowns. You can't solve it. It is with QD and T. And also when you apply the second set of values to the same equation, again, you have two unknowns, isn't it? So you can make two equations and there are two unknowns. So we should be able to solve this two simultaneous equations and find the two unknowns. Am I right? So how can we write it? I'll give you time, you do it by yourself. So we can write ln d1 is equals to ln d naught minus qd over rt1 as one equation. So this is my first equation. Again, I can write ln d2 is equals to ln d naught minus qd rt2. So this is my second equation. So d1, d2, this is first and second two sets of values. Yes. No, 650 is in degree Celsius. When you add 273, that will make the kelvins. So it is 923 kelvins. Is that right? 923 when you add 650 and 273, is that next to 923? So you make the, we make the, yes, temperature to kelvins. So how can we solve the two simultaneous equations? So we can write it. I'm going to write it again. And the next one will be ln d2 is equals to ln d naught minus qd over rt. So this is my first equation. This is my second equation. If I do 1 minus 2, what will happen? I can get rid of d naught, isn't it? D naught term will go. So I have ln d1 minus ln d2 is equals to, so this is a negative. So that will be qd over rt2 minus qd over rt1. Is this right? Now you can make this to qd over r 1 over t2 minus 1 over t1. So everything known in this except the QD. So you can make the QD the subject. So if you make the QD as the subject in this one, what you get? So you have ln d1 minus ln d2. You need to times that by r and divided by 1 over t2 minus 1 over t1. Is that right? So you just need to put the values. When you are putting the values, make sure that your temperature is in Kelvin. So you convert this to Kelvins, 923 and 1173. Yes, so can you guys find me this? I need to know this. Okay, so I will collect your bonus question. We didn't collect the bonus question last week as you had the quiz. So you can hand in it. I'm not marking your papers. I handed in your papers to the person who is marking. It will take about two weeks. R is gas constant. R value is known. R value is R is this, okay? 8.314 joules per moles per Kelvin. 8.314. It's given, it's a constant here. So R is 8.314. You have the, you guys have the bonus. It's a lot big one. It's not this. It can't be negative. Okay, so what did you get here? What did you get, guys?
I got 2, 7, 9, 6.
That's different. We all should get the same one anyway. So here, I think last class got 198, 800. Do you get the same? Something close? What's that? 200? 200,000 something? 200 point something, yes. So something close to 200,000. Do you all get something close to 200,000?
About 196.7.
Yeah, so it's close to this one, isn't it? 196? 196,783. Okay, so let's take this. Just ignore this one. So we'll take this one. Okay, so joules per mole. Anyone have any question? Now, if you know this, we only found the QD. We need to find D note as well. So now you can plug in this in one of these equations and you can find Or else you can use the other equation. You can either use the one which the ln or else exponent. If you use this one, this is, let's take this set. D is 5.5 times 10 to the negative 16. D naught, this is what we need to find. QD we found 196,783. Temperature is 927. 923. And the R is 8.314. So you put all the values in this one and you can find, make the D node the subject and find me the D node. Okay, I want you guys to put your names.
Sorry.
Mark your names and all 4 of you have this one. 2, 3, 4. So mark the names, please, and please highlight your names that I know. These 4 is okay. Find the D note and let me know when you find it.
I don't think that's a real one.
What do we get?
I got 183 times 10 to the
Okay. 0 point.
163 minus 3. That's the balance. So I use the answer.
That's a good. That's a good. You're excited, so then you already go school.
So one of you have got this one. So how about others?
I did it.
Oh, yes, okay.
I got
7.5. So what else we got? Yeah. What's that?
I call it the son of all. Yeah, I got, I was so long. Crazy. Then that's another one. Yeah. Yeah. Oh, yeah, because I still need spring.
I think the answer is 7.5. Can you check? Yeah, so the answer is 7.5 times 10 to the negative 5. Got it? Are you okay with that? Exponent to the power. Do you do that? To the power. Negative sign. Do you have the negative sign as well? Is this what you have in the calculator? So it is 7.5 times 10 to the negative 5 joules per mole, okay? Now there is another part of the question. So you have already found the D naught and Q. So use that, and they are using these two. They are asking you to find another one, a diffusion coefficient when the temperature is this. So you already know your D naught and Q, isn't it? So using the D naught and Q, you need to find the D for this particular temperature. Again, temperature need to be in kelvins. So you need to add it to 73 here. So you can find D, which is D naught is 7.5 times 10 to the negative 5, exponent negative 196,783 divided by 8.31 times . Is this right? So you find the D for this particular temperature for the same materials. That will be again in joules per mole. Sorry. My the joules per mole is the QD. This one should be meters squared per second. I think I put the meter squared per second. What do we get? 8.3 times 10 to the negative 14. Do we all get that? Are we all good? Any question? All good? How about you guys? Okay, those are the 3 numerical questions we have in the tutorial. Again, I want you to do this bonus question. Again, multiple choice questions, but I want you to write the justification why you select that particular answer. We discuss about the vacancies and the vacancy diffusion and also the interstitial diffusion. So you already know the answers, isn't it? So the movement of atoms in crystal lattice during diffusion is facilitated by electron transfer between atoms, the motion of the dislocations, vacancy defects in the lattice, the presence of grain boundaries. So you can select the right answer with the justification why you select it. Interstitial diffusion occurs when the atoms or small molecules. Boys, we are finishing in 2 minutes, okay? Move from one lattice to site or to another. fill in vacancies in the crystal lattice, migrate along grain boundaries, or occupy interstitial spaces between large atoms. So find the answer with justification. I will collect it next week. Yes. So you don't have classes next week. I will see you week after next week, and have a nice break.